Welcome to Mystery Science Theater presents force diagrams. To understand about force diagrams, we first need to understand about forces. A force is an interaction between two objects that results in a push or a pull. There are two types of forces. We can classify all forces into one of two categories. We call these categories contact forces or long-range forces. Contact forces means that the two objects that are interacting have to be touching. And some examples of common contact forces are things like friction, tension, and then there's a force where a surface is pushing perpendicular to the object. We call that a normal force, and we'll talk more about that here in just a second. So friction, tension, and normal, those are some common contact forces. Another common contact force is one that doesn't really have a special name. For example, if you take your hand and push something with it, we usually just refer to that as an applied force. So we're going to just say applied force is an example of a contact force. Long-range forces, the two objects that interact do not need to be touching. And so we can think of some forces where touching is not required. This involves things like gravity, electric forces, and magnetic forces. Just some examples of long-range forces. And for the purpose of this class, we're not going to worry about electric or magnetic forces. So for our purposes, gravity is going to be the only long-range force that we're going to deal with. And that's really nice for a couple of reasons. One, we always know that gravity is going to be there because the objects are going to have mass. And two, we know what direction it's going to be. It's always towards the center of the Earth. And so for gravity, that's a good force that we can start with. The other nice thing about gravity is that we know that it's going to be the only long-range force we deal with. So once we've accounted for gravity, then we've accounted for all of the long-range forces. So any other force acting on an object must be a contact force. And for there to be a contact force, we can identify what's touching our object that is exerting that force. A force diagram is just a way to diagram the forces. So to draw a force diagram, first thing we do is we identify our system. What object or objects are we studying? So we identify our system. The next thing we do is we diagram long-range forces. Really, again, we're just talking about gravity here. We'll use F sub g. F for force and then G for the specific force, the force of gravity in this case. And then third, we're going to diagram contact forces. And remember, for contact forces, there has to be something touching our object that is exerting that force. Let's do an example. Suppose I have on my table a box. So here's a box sitting on the table. Well, the system is going to be the box. I'm going to represent the system with a dot. So here is my force diagram that represents my box, my system. Next, I'm going to diagram long-range forces, the force of gravity. I know that it's downward, and I'm going to label that FG. So I use a downward arrow to indicate the direction. The length of the arrow indicates the magnitude or the size of the force, and the direction points obviously in the direction. Now, it's touching this table, and so I know that there is also an upward force exerted by the table perpendicular to the surface, and that is what we call a normal force. So here is the normal force. So this is just an example of what a force diagram is going to look like. So the key is identify the system, diagram the long-range forces, diagram the contact forces. To do this, it's going to be important to make sure that we look at Newton's second and first laws. If an object is accelerating, then we know the forces are not balanced. If the object is not accelerating, we know that the forces must be balanced. So let's take a look here. So this sample here, the object is motionless. That was the example we just did. Dot to represent our system, the box. We draw our force of gravity, which is downward. It is not accelerating, so I know that the forces are balanced. So the table must be pushing up with an equal amount of force, and that is a normal force. But what about this case right here? Object slides at constant speed without friction. Well, our system is our box. So here we go. There's our system. I know there's a force of gravity pointed down. And what's touching the box? Well, the surface is touching the box, and so there's a normal force perpendicular to the surface, and that's going to be up like so. And then it's sliding at constant speed without friction. So I know there's no friction, and the surface can exert a normal force and a friction force, but there's no friction, and I've got my normal. Now that's it. There's no other force acting on it. How do I know that? Because nothing else is touching it. Notice the force diagram for the object sliding at constant speed without friction is exactly the same as the force diagram for the object that lies motionless. That's because Newton's first law says that an object in motion will remain in motion unless acted upon by an unbalanced force. So here we have an object in motion. It's just going to keep going, constant speed, unless there's some unbalanced force to change its motion. Now let's look at this one. Object slows due to kinetic friction. So here, there's my system. Force of gravity, normal force, perpendicular to my surface. Now it says there is friction. Friction will be opposing the motion. So there's my friction force. Notice there's nothing pushing it to the right. So the forces are not balanced. That's okay because I know it's slowing down. In other words, it is accelerating. So I know that the forces should not be balanced. Let's look at this one. Object slides without friction. Start with my system here. Have my force of gravity, which is straight down, and then perpendicular to the surface, I'm going to have a normal force. There is no friction, so that's it. Notice they're not balanced because they're not in the same direction, so they don't cancel each other out completely, and that's okay, because if it's sliding without friction, I know that this is going to accelerate, and so I expect the forces not to be balanced. How about this one, where static friction prevents sliding? There's my system there, the box. Force of gravity touching the surface, so I've got a normal force perpendicular, and there's a friction force parallel to the surface, like so. And those are going to be balanced because it's not sliding, it's not accelerating. How about this next one? There's a string. Well, I start with my system, force of gravity down. Now what's touching my box here? The string is touching the box. What kind of force does a string exert? That's a tension force. So we'll call that Ft for tension force there. And that's it. There's nothing else touching it. So that's what the diagram looks like for that. How about this one? There's my box, the system. Force of gravity. Now I've got two strings. I've got two tensions. One tension is going over here in that direction of the string, and the other tension is going up here in the direction of that string. And there we have it. Similarly, this one, force of gravity down. I've got one tension in the direction of this string and one tension in the direction of this string. I might call that Ft1 and Ft2 just so I can keep track of the different tensions there. Okay? Let's look at another example. How about this one? Object is pulled by a force at an angle to the surface. Okay? So I know, I'm just going to draw this one out in the margin here. There's my box, there's my object. I know there's a force of gravity. I'll draw that one first. Now, if there is an applied force that's given, I like to draw that second. After gravity, draw this applied force F, and it's labeled in the diagram just F, so I'm just going to call it F. That's my applied force F. Now, what else is touching my box here? Well, this surface is. Surface can exert friction and normal forces. So I know there's going to be a normal force and a friction force. Now, in this problem, I don't know if it's accelerating or not. And if I don't, I'm just going to, I'm going to assume one way or the other, and that's okay. But notice the normal force is not the same size as the force of gravity. Why not? Because this applied force has an upward part of it. And because there's some upward part to this applied force, it's the up together, the normal force plus this y component of this applied force, that has to equal the downward force of gravity. Because it's definitely not accelerating in the vertical direction, so I know those vertical forces have to balance. So here the normal force is actually less than the force of gravity. Let's look at this example down here. Okay, in this case, the applied force is being pushed at a downward angle instead of being pulled at an upward angle. Well, there's still the force of gravity, which is straight down. Next, I'm going to draw this applied force. It's pushed down and to the left. So I'm going to label that. There's my applied force. Then I've got some friction parallel to my surface and resisting the motion. And my normal force, you'll notice in this case, happens to be much larger than my force of gravity. One other one I want to look at here is this one. The ball is rising in a parabolic trajectory. So we shoot a basketball, or a baseball is hit, a fly ball. So it's on its way up. Well, the ball is my system, and I know there is a force of gravity going to be downward. Okay, and what's touching the ball? Nothing. Well, the air is touching it, but if we assume air resistance to be negligible, then nothing else is touching the ball. There is no other force. That's it. It's just the force of gravity. I hope this makes sense, and I hope that you have learned a little bit about drawing force diagrams. Thank you. Enjoy.